Welcome to Animal Uncovered, the podcast where we explore the most unbelievable life cycles in the natural world. From the moment life begins to the moment it ends, nothing is as simple as it seems. The dawn light barely penetrates the surface as she glides through the cobalt depths, 200 meters down off the coast of Cocos Island. She's not alone. Around her, dozens of others move in formation, a living constellation of strange, prehistoric forms wheeling through the thermocline. Each one bears the same bizarre profile. A head flattened and stretched like a medieval warhammer, eyes positioned at impossible angles, a body that seems sculpted by nightmare and genius in equal measure. The great Hammerhead has been hunting since before sunrise, her sensors firing across a neural network that makes our most advanced technology seem primitive. She detects the faint electrical whisper of a stingray buried 30 centimeters beneath the sand, a pulse of bioelectricity no stronger than a half-volt, invisible to every other predator in these waters. But to her, it blazes like a beacon. She descends with mechanical precision, that extraordinary head sweeping across the seafloor like a metal detector. The stingray, feeling vibrations through its buried sanctuary, bolts from its hiding place, but it is already too late. In one fluid motion, she pins the fleeing ray against the bottom with the edge of her cephalofoil, using her head as both sensor array and weapon. The ray's venomous barb slashes across her face, leaving a wound that would incapacitate most predators. She doesn't flinch. Her skin is thick with dermal denticles, and she has survived dozens of such encounters. Pain is simply information. She adjusts her grip, crushes the ray's wing, and begins to feed. This is not a monster. This is not an aberration. This is 400 million years of evolution compressed into a single, perfect hunting machine. A creature so exquisitely adapted to its environment that it has become one of the ocean's supreme predators. And yet, for all its advantages, the hammerhead shark faces a paradox. The very adaptations that make it magnificent also make it vulnerable in ways that most sharks are not. Part 1. Why this animal matters. When most people picture a shark, they imagine something sleek and torpedo-shaped. The great white, perhaps, or the tiger shark with its blunt snout and powerful jaws. The hammerhead challenges every assumption we have about what a predator should look like. Its head, that remarkable, laterally flattened structure called a cephalofoil, appears so improbable that early naturalists struggled to explain it. Was it a deformity? An evolutionary accident? A cruel joke played by nature? The truth, as is so often the case, is far stranger and more elegant than fiction. There are 9 species of hammerhead shark, ranging from the diminutive bonnethead, barely longer than a human arm, to the great hammerhead, which can exceed 6 meters in length. Each species displays a variation on the same improbable theme, a head that extends laterally, creating a living hydrofoil, studded with some of the most sophisticated sensory organs in the animal kingdom. The great hammerhead, the smooth hammerhead, and the scalloped hammerhead are the most familiar, apex predators that patrol tropical and warm temperate waters across every ocean on Earth. But why the hammer? This question has occupied marine biologists for over a century, and the answers reveal something profound about the nature of evolutionary innovation. The cephalofoil is not one adaptation, but many, woven together into a structure that serves multiple overlapping functions. It is a sensory platform, expanding the surface area available for electroreceptors called ampullae of Lorenzini, organs that detect the minute electrical fields generated by all living things. It is a hydrodynamic wing, providing lift and enhanced maneuvering capability. It is a weapon used to pin and disorient prey. And recent research suggests it may even serve as a thermal regulator during deep dives. The hammerhead has taken the basic shark body plan, already one of nature's most successful designs, virtually unchanged for hundreds of millions of years, and modified it in a way that seems to defy logic. And yet, it works. It works so well that hammerheads have persisted through ice ages and mass extinctions, through the rise and fall of countless marine ecosystems, maintaining their dominance even as the oceans transformed around them. But dominance comes at a cost. The hammerhead's extraordinary adaptations require trade-offs. That massive head creates drag, demanding more energy to maintain swimming speed. The specialized hunting strategies make hammerheads dependent on specific prey species, and perhaps most critically, their reproductive biology. Like all sharks, hammerheads bear live young rather than laying eggs, means they reproduce slowly, making them vulnerable to overfishing in ways that bony fish are not. Today, every species of hammerhead shark is either threatened or endangered. The great hammerhead, that supreme predator we met in our opening, is critically endangered, the highest category before extinction. In some regions, populations have declined by over 90% in just 3 decades. The central question of this episode is not simply how the hammerhead lives, but how something so perfectly adapted, so exquisitely tuned to its environment, can be brought to the edge of extinction in what amounts to an evolutionary eye blink. To understand that, we must first understand the life cycle itself, from the moment of conception to the day a hammerhead meets its end. Part 2. Evolution and Origins. The story of the hammerhead begins approximately 20 million years ago during the Miocene epoch, when the Earth's oceans were warmer than they are today, and the Panama Isthmus had not yet closed, allowing water to flow freely between the Atlantic and Pacific. The ancestors of modern hammerheads were not so different from contemporary Carcharodonid sharks, the family that includes bull sharks, tiger sharks, and reef sharks. They had the standard predatory profile: streamlined bodies, powerful tails, forward-facing eyes, and mouths filled with serrated teeth. But evolution is fundamentally opportunistic. It seizes on random mutations, testing them against the crucible of survival. And somewhere in the tropical shallows of the Proto-Atlantic, a mutation occurred that would change the shark world forever. The first proto-hammerheads likely displayed only a modest lateral expansion of the head, perhaps just a slight flattening, barely noticeable. But that small change would have had profound effects. By spacing the eyes farther apart, it increased binocular overlap in the vertical plane, allowing better depth perception when hunting prey on the seafloor. By expanding the surface area of the head, it created more space for ampullae of Lorenzini, those remarkable electroreceptors that can detect voltage gradients as small as 5 nanovolts per centimeter. In the competitive environment of the Miocene, where predators jostled for ecological niches and prey species were evolving ever more sophisticated defenses, even a modest advantage could mean the difference between starvation and success. The proto-hammerheads with slightly wider heads were better at finding hidden prey. They caught more food, survived longer, and produced more offspring. Their genes spread through the population. Natural selection amplified the trait. Over millions of years, through countless generations, the head grew wider. The eyes migrated farther apart. The nostrils, which sharks use to detect chemical traces in the water, spread to the lateral extremes of the cephalofoil, allowing the animals to sample a larger volume of water with each sweep of the head. The structure became more refined, developing hydrodynamic properties that reduced energy costs and increased maneuverability. Fossil evidence for this transition is frustratingly sparse. Shark skeletons are made of cartilage, which rarely fossilizes, leaving us with mostly teeth and occasional vertebrae. But molecular studies allow us to reconstruct evolutionary relationships with remarkable precision. By comparing DNA sequences across living shark species, scientists have determined that the hammerhead family, Sphaernidae, diverged from other Carcharodonid sharks sometime between 20 and 25 million years ago. The family then rapidly diversified into the 9 species we see today, each adapting to slightly different ecological niches. The winghead shark, found in the Indo-Pacific, developed the most extreme cephalofoil proportions. Its head can be up to half its body length. The bonnethead, found in coastal waters of the Americas, has a relatively modest shovel-shaped head and has even evolved the ability to digest seagrass, making it possibly the only omnivorous shark. The great hammerhead became the apex predator, specializing in large prey including other sharks and rays. What's remarkable is how recently all of this occurred. 20 million years is a geological instant. Sharks as a group have existed for over 400 million years. They predate trees, predate dinosaurs, predate the colonization of land by vertebrates. The hammerhead, in evolutionary terms, is a newcomer, an upstart, a radical experiment in body architecture, and yet it has become one of the ocean's most successful predators. But success is never permanent. Evolution doesn't care about preservation. It cares only about what works right now, in this moment, in this environment. The hammerhead's triumph was built on specific conditions: abundant prey, stable ocean temperatures, healthy reef and coastal ecosystems. As we will see, when those conditions change, even 400 million years of sharkhood cannot guarantee survival. Part 3. The Life Cycle. Phase 1. Conception and Gestation. The life of a hammerhead shark begins not with an egg laid on the seafloor, but inside the body of its mother, a female who may be anywhere from 15 to 30 years old, having reached sexual maturity only after more than a decade of growth. This is the first critical fact of hammerhead biology. They are ovoviviparous, meaning the eggs develop and hatch internally, with the young nourished first by a yolk sac and later by a placental connection that transfers nutrients directly from mother to embryo. Mating among hammerheads is a violent affair, though perhaps no more so than in most shark species. During the mating season, which varies by species and location, but often occurs in spring and summer, males pursue females aggressively, biting them on the pectoral fins and body to maintain their grip during copulation. Female hammerheads have evolved thicker skin than males, specifically as a defense against this rough courtship. The male inserts one of his 2 claspers, specialized pelvic fins modified for internal fertilization, and transfers sperm packets called spermatophores. What happens next is remarkable. The female stores the sperm in her oviducal gland, where it can remain viable for weeks or even months. This delayed fertilization allows her to time embryonic development with optimal environmental conditions, waiting until water temperatures are right, until prey is abundant, until the seasonal movements of her species bring her to safe birthing grounds. Once fertilization occurs, the embryos begin to develop. In the great hammerhead, gestation lasts approximately 11 months, nearly as long as a human pregnancy. During this time, the female must eat enough not just to sustain herself, but to nourish a litter of 20 to 50 developing pups, each growing from a fertilized egg smaller than a grain of rice to a fully formed shark nearly 70 centimeters long. The developing embryos face their first existential challenge before they're even born: intrauterine cannibalism. In some shark species, the strongest, fastest developing embryos will consume their weaker siblings inside the womb. While this is less common in hammerheads than in species like sand tigers, where only 2 pups, one from each uterus, survive to birth, there is still competition for resources. The strongest embryos position themselves closest to the placental connection, receiving more nutrients and growing faster. Throughout gestation, the female continues her normal patterns, hunting, migrating, evading predators. But she carries an enormous burden. A pregnant great hammerhead may carry up to 50 kilograms of developing pups, roughly 10% of her body weight. This affects her swimming efficiency, her ability to hunt, her vulnerability to larger predators. She must balance the energetic demands of pregnancy against the need to feed herself and avoid becoming prey. Phase 2. Birth in the first hours. After nearly a year, the female enters shallow protected waters, often coastal bays, lagoons, or the mouths of estuaries where fresh water mixes with salt. These nursery grounds are chosen with precision. They must be shallow enough to exclude most large predators, but deep enough for the mother to maneuver. They must be rich in small prey, fish, crustaceans, mollusks, that the newborn pups can hunt, and they must be relatively warm, as newborn sharks have less efficient thermoregulation than adults. Birth occurs live. The pups emerge tail first from the mother's cloaca, one by one over a period of several hours. Each pup is fully formed, a miniature replica of the adult, complete, with that distinctive hammer-shaped head. But unlike many mammals, there is no parental care. The moment the pup is born, it must fend for itself. The mother does not protect it, does not teach it to hunt, does not even acknowledge its existence. Indeed, if the pup is not quick enough to escape, the mother may cannibalize it, not out of cruelty, but simply because it registers as potential food, and she has expended enormous energy during pregnancy. This is the brutal calculus of our selection, an evolutionary strategy that prioritizes producing many offspring with minimal investment in each one. The hammerhead mother has done her part by gestating the pups for 11 months and delivering them to a safe nursery ground. Now their survival is their own responsibility. The first hours of life are critical. The newborn pup, still trailing remnants of the umbilical connection, must immediately begin swimming. Sharks, unlike bony fish, do not have swim bladders to maintain neutral buoyancy. They must swim constantly or sink to the bottom. The pup's muscles, though functional, are weak. Its hammer-shaped head, though smaller and proportionately less extreme than an adult's, still creates drag. It must reach the surface to orient itself, must find shelter among the seagrass or mangrove roots, must begin hunting within the first 24 hours. Many pups do not survive this transition. Some are born weak, unable to swim effectively. Some emerge in the wrong location, too deep, too exposed, too far from shelter. Some are picked off by opportunistic predators, large fish, other sharks, even seabirds that plunge into the shallows to snatch a newborn in their beaks. Mortality in the first week of life may exceed 50%, but those that survive, the strong ones, the lucky ones, begin to feed. Phase 3, Juvenile Phase. For the first several years of life, juvenile hammerheads inhabit shallow coastal waters, rarely venturing into the open ocean. This is both a refuge and a prison. The shallow water protects them from larger pelagic predators, but it also concentrates them in areas where human activity is most intense. Fishing, boat traffic, coastal development, pollution. The young hammerhead feeds opportunistically. Its diet consists primarily of small fish, shrimp, crabs, and mollusks, whatever it can catch with its still developing hunting skills. The cephalofoil, even in a juvenile, is a sophisticated sensory tool. The pup swings its head from side to side as it swims, scanning the seafloor for the electrical signatures of buried prey. When it detects something, a shrimp hidden in the sand, a small fish resting in the seagrass, It investigates with its entire head, using the ampullae of Lorenzini to triangulate the precise location. But the young hammerhead is not yet an efficient hunter. It misses more often than it catches. It expends energy chasing prey that eludes it. It misjudges distances, mistimes attacks, gets confused by false signals. Hunting is a learned skill, refined through thousands of attempts. The pups that learn fastest, that develop better strategies, that remember which techniques work and which don't. These are the ones that grow quickly and survive. Growth is paramount. A larger shark is a safer shark. Size deters predators, expands the range of available prey, and determines position in the social hierarchy of juvenile hammerheads, which often school together in groups of dozens or even hundreds. These aggregations are not familial. The pups have no way of recognizing siblings, but rather opportunistic gatherings where safety in numbers reduces individual predation risk. As the hammerhead grows, it faces new challenges. Its metabolism is high, requiring constant food intake. It must avoid a gauntlet of predators, larger sharks, including other hammerheads, groupers and other large reef fish, dolphins, which are known to kill small sharks, and, increasingly, humans. Commercial fishing operations using long lines, gill nets and trawls kill millions of juvenile sharks every year, including hammerheads. The juvenile phase is also when the hammerhead's unusual morphology creates specific vulnerabilities. That wide head increases drag, making the young shark less energy efficient than more streamlined species. It makes quick acceleration more difficult, and it makes the hammerhead particularly susceptible to becoming entangled in fishing nets. The cephalofoil catches in the mesh, and the shark, unable to swim backward like bony fish, becomes trapped and drowns. Despite these challenges, many hammerheads survive to adolescence. By age 5 or 6, a scalloped hammerhead may be 2 meters long. A great hammerhead might reach 2.5 meters. They are no longer vulnerable to most predators, save for large sharks and orcas. They begin to expand their range, venturing into deeper water, exploring new hunting grounds. But they are not yet mature. Sexual maturity in hammerheads does not occur until the late teenage years, 15 to 18 years for great hammerheads, 10 to 12 for scalloped hammerheads. This is one of the slowest maturation rates of any shark species, and it represents a fundamental vulnerability. Predators with slow maturation and low reproductive rates cannot withstand high levels of mortality. If too many juveniles are killed, the population cannot replace itself. Phase 4 – Maturity and Adulthood. When a hammerhead finally reaches sexual maturity, it enters what should be the prime of its life, a period lasting perhaps 2 decades, during which it is too large for most predators, but still vigorous enough to hunt effectively and compete for mates. Mature hammerheads are formidable predators. A great hammerhead at full size, 4 to 6 meters long, weighing up to 450 kilograms, can take prey that few other sharks would attempt. Stingrays are a favored target despite their venomous barbs. Eagle rays, guitarfish, even smaller sharks, all fall prey to the great hammerhead's combination of sensory acuity and brute force. The hunting technique is precise. The hammerhead approaches the seafloor with its head angled down, sweeping it side to side in wide arcs. The ampullae of Lorenzini, which number in the thousands, far more than in non-hammerhead sharks, create a 3-dimensional electrical map of the environment. The shark can detect not just the presence of prey, but its orientation, its state of activity, even, possibly, its species. When a stingray is located, the hammerhead positions itself above the buried fish and descends rapidly. It uses the leading edge of its cephalofoil, thick with cartilage and covered in abrasion-resistant skin, to pin the ray against the bottom. The ray thrashes, often driving its barb into the hammerhead's head or body. But the hammerhead has evolved a remarkable tolerance for these injuries. Researchers examining great hammerheads have found individuals with dozens of barbs embedded in their mouths and faces, evidence of a lifetime of successful hunts. Once the ray is pinned, the hammerhead repositions and bites, using powerful jaws lined with triangular, serrated teeth to crush through cartilage and muscle. A large hammerhead can bite through the pectoral disc of an eagle ray, a structure analogous to a wing made of tough cartilage, as easily as we might bite through a cracker. But hammerheads are not mindless eating machines. They demonstrate strategic thinking, memory, and perhaps even cultural transmission of hunting techniques. Scalloped hammerheads at certain locations have learned to feed on bottom-dwelling octopuses, using specific techniques to extract them from rocky crevices. In other regions, hammerheads have been observed hunting cooperatively, herding schools of fish into tight pools before attacking. During this mature phase, hammerheads also engage in complex social behaviors. Scalloped hammerheads, in particular, are highly social, forming aggregations of hundreds of individuals around seamounts and underwater plateaus. These gatherings serve multiple purposes: mate selection, information transfer about food sources, and, possibly, simply the advantages of group living. The social structure within these schools is sophisticated. Larger females tend to occupy central positions, while smaller individuals remain at the periphery. There are dominance hierarchies established and maintained through body language, specific swimming patterns, head movements, and, when necessary, aggressive displays. Mating occurs within these aggregations, with dominant males gaining access to the best females. For 20 years, perhaps 30, a mature hammerhead patrols its range, hunting, mating, surviving. It accumulates scars, wounds from prey, from rivals, from encounters with predators. Its teeth are replaced continuously, with some species of sharks cycling through 30,000 teeth in a lifetime. It grows slowly but steadily, never quite stopping, though growth rate declines dramatically after maturity. But age brings its own challenges. Phase 5. Senescence and Death. Sharks do not age like mammals. They do not experience the rapid physiological decline, the loss of muscle mass, the organ failure that characterizes old age in terrestrial vertebrates. Some species of shark may be functionally immortal, showing no signs of senescence at all. Greenland sharks, close relatives of the hammerhead, can live for over 400 years, with the oldest known individual estimated at 512. But hammerheads, despite their evolutionary sophistication, do age. Older hammerheads swim more slowly, their reflexes dull, their wound-healing capacity declines. An injury that a young shark would recover from in weeks may take months in an old individual, or may never fully heal. The oldest great hammerheads may reach 40 or 50 years of age, though in the modern ocean few survive past 30. Scalloped and smooth hammerheads live somewhat shorter lives, perhaps 30 to 40 years under optimal conditions, but optimal conditions are increasingly rare. Death for a hammerhead shark can come in many forms. Predation by orcas remains a threat throughout life. These intelligent, cooperative predators have learned to flip sharks onto their backs, inducing tonic immobility, a trance-like state, before drowning them or extracting their nutrient-rich livers. Large great whites and tiger sharks will opportunistically attack hammerheads. Disease and parasites take their toll, particularly on older, weakened individuals, but increasingly, death comes from human activity. Hammerheads are particularly vulnerable to longline fishing, which targets oceanic predators using thousands of baited hooks suspended from miles of line. The hammerhead's wide head makes it difficult for the shark to maneuver away from the hooks, and its strong swimming causes it to entangle itself further. Even if released alive, the stress of capture, combined with lactic acid buildup from struggling against the line, often proves fatal within hours. Gill nets are even deadlier. These walls of invisible mesh stretched across migration routes trap hammerheads by their cephalofoil. Unable to ram backward through the net, the shark drowns. In some regions, gill nets targeting other species kill hammerheads as bycatch at unsustainable rates. And then there is the deliberate harvest. Hammerhead fins are among the most valuable in the global fin trade. The fins, dried and sold to Asian markets, fetch premium prices because of their size and the quality of the cartilage strands called fin rays, used in shark fin soup. A single large hammerhead's fins can be worth hundreds of dollars to a fisherman, while the rest of the body, less valuable, is often discarded at sea. When a hammerhead dies naturally from age, disease, or predation, its body does not go to waste. It sinks to the seafloor, where it becomes a bonanza for scavengers. Hagfish, crabs, and amphipods descend upon the carcass, stripping flesh from cartilage. Larger scavengers, other sharks, rays, groupers, tear away chunks of muscle. Within days or weeks, depending on depth and temperature, the shark is reduced to scattered bones, and then even these are consumed, broken down by bacteria, returned to the nutrient cycle. This is the way it has been for millions of years. Predators dying, their bodies nourishing the ecosystems they once dominated. The atoms that made up their flesh, redistributed through food webs, incorporated into new life. It is efficient, cyclical, sustainable. But sustainability requires that enough hammerheads survive to reproduce before they die. And this is where the modern hammerhead faces its greatest challenge. Part 4. Biology and Adaptations. To understand why hammerheads are so vulnerable despite being so well adapted, we must examine the very adaptations that make them successful. The cephalofoil. The hammerhead's head is not simply wide, it is a precision instrument. The cephalofoil serves as a multi-function sensor platform, hydrodynamic surface, and weapon, all integrated into a single structure. The ampullae of Lorenzini are the most remarkable feature. These are gel-filled pores connected to electroreceptive cells that detect voltage gradients in seawater. All sharks possess these organs, but hammerheads have refined them to an extraordinary degree. The ampullae are concentrated on the ventral surface of the cephalofoil, giving the hammerhead an electrical sensitivity that exceeds that of nearly any other predator. This ability allows hammerheads to hunt prey that other sharks cannot find. A stingray buried in sand produces no visual cue, no sound, almost no scent, but it cannot hide its electrical signature. Every muscle contraction, every heartbeat, every nervous impulse generates a tiny electrical field that propagates through the conductive medium of seawater. To a hammerhead, it might as well be waving a flag. Recent research has revealed that the shape of the cephalofoil is also optimized for hydrodynamics. When a hammerhead swims, the head functions as a forward-mounted wing, generating lift and allowing the shark to make tighter turns than would otherwise be possible. This is critical when hunting agile prey. A scalloped hammerhead chasing a school of fish can change direction with remarkable speed, using its head to bank and pivot like an aircraft. But there are costs. That wide head creates drag, increasing the energy required to swim. Hammerheads must feed more frequently than more streamlined sharks to maintain their metabolic rate. They must be in constant motion, not just to breathe. Like all sharks, they need water flowing over their gills, but to offset the drag penalty of their unusual shape. Dentition and diet. Hammerhead teeth reflect their dietary specialization. Unlike the great white's massive triangular teeth designed for tearing flesh from large prey, or the mako's narrow dagger-like teeth for grasping fast-swimming fish, hammerhead teeth are smaller, more numerous, and designed for crushing and grinding. The great hammerhead, despite being an apex predator, has relatively modest teeth, roughly 2 centimeters in height, triangular with serrated edges, arranged in multiple rows. But these teeth are backed by immensely powerful jaws. The bite force of a large great hammerhead has been estimated at several hundred kilograms, sufficient to crack through the cartilaginous skeleton of a stingray or the shell of a sea turtle. Teeth are replaced continuously. Each functional tooth is backed by several replacement teeth that move forward on a conveyor-like system, as older teeth are lost through wear or breakage. A hammerhead may go through thousands of teeth in its lifetime, each tooth lasting only weeks or months before being shed and replaced. Respiration and metabolism. Hammerheads are obligate ram ventilators, meaning they must swim constantly to force oxygenated water over their gills. They cannot rest on the seafloor like some benthic sharks, cannot pump water through their mouths while stationary. If a hammerhead stops swimming, it suffocates. This creates a perpetual energy demand. Even at rest, which for a hammerhead means cruising at low speed, the shark is burning calories. During active hunting or when evading predators, the metabolic rate skyrockets. Hammerheads must therefore be efficient hunters, maximizing caloric intake relative to energy expenditure. One adaptation that helps is the ability to perform deep dives. Scalloped hammerheads have been tracked diving to depths exceeding 800 meters, well into the oxygen minimum zone where the water is cold and dark. These dives may serve multiple purposes, accessing deep water prey, thermoregulation, or predator avoidance. But deep diving is metabolically expensive, and the shark must warm up after returning to the surface. Recent studies suggest that the cephalofoil may play a role in thermoregulation. By increasing blood flow to the head during deep dives, the hammerhead may be able to dump excess heat before returning to the cold depths. Alternatively, by reducing blood flow, it may minimize heat loss to the surrounding water. Reproduction. Hammerheads reproduce slowly. Great hammerheads reach sexual maturity at 15 to 18 years of age, produce litters every 2 years, and each litter, though large by shark standards, still represents a tiny fraction of the reproductive output of bony fish. A single female great hammerhead might produce only 200 pups in her lifetime, and most of those pups will die before reaching maturity. This reproductive strategy, called K-selection, works well in stable environments where adult mortality is low. The strategy assumes that a female will have decades to reproduce, that she will successfully give birth multiple times, and that at least a few of her offspring will survive to carry on her genes. But K-selection is catastrophically vulnerable to increased mortality. If adults are being killed faster than they can reproduce, which is exactly what happens under intensive fishing pressure, the population enters a death spiral. Juvenile survival rates cannot compensate for adult losses because juveniles are being killed as well, before they ever have a chance to reproduce. This is the fundamental reason why hammerhead populations are collapsing worldwide. Their biology, so exquisitely tuned to life as apex predators in a stable ocean, has become a liability in an ocean dominated by industrial fishing. Part 5. Ecosystem Role. Hammerhead sharks occupy a unique position in marine ecosystems. As apex predators and mesopredators, depending on size and species, they exert what ecologists call top-down control. regulating populations of prey species and indirectly shaping the entire community structure of coral reefs, seagrass beds, and coastal ecosystems. Consider the great hammerhead's preference for rays. By preying on stingrays and eagle rays, hammerheads prevent these animals from overpopulating and decimating populations of bottom-dwelling invertebrates, the mollusks, crustaceans, and worms that rays consume in vast quantities. These invertebrates, in turn, play crucial roles in nutrient cycling, sediment mixing, and as prey for other species. When hammerhead populations decline, ray populations explode, a phenomenon documented along the US East Coast, where hammerhead numbers have dropped by over 90% since the 1980s. The resulting increase in Konos rays led to the collapse of century-old scallop fisheries in North Carolina. The rays consumed scallops faster than the shellfish could reproduce, destroying both an ecosystem and a human livelihood. This cascade effect, where the removal of a top predator triggers changes that ripple through multiple trophic levels, is called a trophic cascade, and hammerheads are powerful cascade initiators. Their role goes beyond simple predation. By altering the behavior of prey species, causing rays to spend less time in vulnerable habitats, forcing fish to school more tightly, hammerheads shape the spatial distribution and habitat use patterns of dozens of other species. Scalloped hammerheads, with their tendency to form large aggregations, play another crucial role: nutrient transport. During the day, schools of hammerheads rest around seamounts and offshore islands. At night, they disperse to hunt in coastal waters and over continental shelves. In the process, they transport nutrients from productive coastal zones to nutrient-poor offshore waters via their waste products. This vertical and horizontal nutrient pumping can be significant, particularly around isolated oceanic islands where hammerheads are abundant. Hammerheads also serve as hosts for numerous parasites, copepods, isopods, cestodes, nematodes, and while we typically think of parasites as detrimental, they are actually integral parts of healthy ecosystems. Parasites regulate host populations, transfer energy between trophic levels, and contribute to biodiversity. The parasites of hammerhead sharks, in turn, have their own complex life cycles involving intermediate hosts, free-living stages, and intricate adaptations. In essence, hammerheads are keystone species, organisms whose impact on the ecosystem is disproportionate to their abundance. Remove the keystone and the arch collapses. This is not hyperbole. In regions where hammerheads have been locally extirpated, scientists have documented fundamental changes in ecosystem structure, shifts in species composition, declines in overall biodiversity, increased prevalence of disease, and loss of ecological resilience, the ability of an ecosystem to absorb disturbance and maintain its essential functions. The ocean, it turns out, needs its hammerheads. Part 6. Human Connection and Conservation. Humans and hammerheads have a long, complex relationship, one that has shifted dramatically in recent decades from reverence to exploitation. In many Pacific Island cultures, hammerhead sharks are revered as umawa, ancestral guardians, physical manifestations of family gods. In Hawaiian tradition, the hammerhead, called mano kihikihi, is associated with strength and protection. To harm a hammerhead was to offend one's ancestors, inviting supernatural retribution. Similar beliefs exist in other Polynesian cultures, where sharks are seen as protectors of fishermen, guides to safe waters, and symbols of martial prowess. These cultural attitudes fostered a relationship of respect. Sharks were sometimes hunted, but with ceremony and restraint in numbers that ecosystems could sustain. The harvest was for subsistence, for meat, for skin, for teeth used in weapons and ornaments, not for profit. That changed with industrialization. The development of large-scale fishing fleets in the mid-20th century, combined with growing global demand for shark products, transformed the relationship. Hammerheads, which aggregate predictably and inhabit coastal waters where fishing pressure is intense, were particularly vulnerable. The primary threat is finning. The practice of removing a shark's fins and discarding the rest of the body at sea. Shark fins are valuable, shark meat less so. By keeping only the fins, a fishing vessel can maximize profit per unit of storage space. The hammerhead, unable to swim without its fins, sinks to the seafloor and dies slowly of suffocation. The scale of the trade is staggering. Estimates suggest that between 63 million and 273 million sharks are killed annually for their fins, with hammerheads representing a significant portion. The great hammerhead's large, distinctive fins are especially prized. A single fin set can sell for over $200 at the dock, escalating to thousands of dollars in retail markets. Beyond finning, hammerheads face threats from bycatch, incidental capture in fisheries targeting other species. Gill nets, long lines, and trawls kill millions of sharks each year. Hammerheads, with their wide heads, are particularly prone to entanglement. Studies suggest that scalloped hammerheads have the highest post-release mortality rate of any shark species caught on long lines. Even when released alive, the stress and injury often prove fatal. Habitat degradation compounds these pressures. Hammerheads depend on coastal nursery areas, mangrove forests, estuaries, seagrass beds that are being destroyed at alarming rates by coastal development, pollution, and aquaculture. The juveniles that would have found refuge in these habitats are now exposed to predators and environmental stressors. Climate change adds another layer of threat. Rising ocean temperatures are shifting the distribution of prey species, forcing hammerheads to alter their migration patterns and potentially bringing them into conflict with fisheries. Ocean acidification may affect the development of hammerhead embryos and the availability of prey species with calcium-based shells or exoskeletons. The result is a perfect storm of anthropogenic pressures. Hammerhead populations have declined catastrophically in nearly every region where data exist. The great hammerhead is classified as critically endangered by the International Union for Conservation of Nature. One step from extinction in the wild, the scalloped hammerhead is critically endangered in some regions, endangered globally. Even the smooth hammerhead, once considered common, is now listed as vulnerable. In the Gulf of Mexico, scalloped hammerhead populations have declined by over 95% since the 1980s. Similar declines have been documented in the Mediterranean, the Red Sea, and along the US East Coast. In some areas, hammerheads have been functionally extirpated. They still exist, but in numbers so small they no longer fulfill their ecological role. Yet there are glimmers of hope. Conservation efforts are beginning to bear fruit. Several countries have banned shark finning, requiring that sharks be landed with fins attached, making the practice economically unviable. Marine protected areas have been established in key hammerhead habitats, including around the Galapagos Islands, Cocos Island, and Malpelo Island, where scalloped hammerheads gather in massive aggregations. International trade in hammerhead fins is now regulated under CITES, the Convention on International Trade in Endangered Species, meaning that any international shipment must be accompanied by documentation proving the fins were harvested legally and sustainably. While enforcement remains imperfect, this represents a significant step. Scientific research has accelerated. Tagging studies using satellite transmitters have revealed hammerhead migration patterns, allowing scientists to identify critical habitats and migration corridors that need protection. Genetic studies have clarified population structure, showing that different regions harbour genetically distinct populations that should be managed separately. And public awareness is growing. Campaigns highlighting the plight of hammerheads have reached millions of people, shifting consumer behaviour and generating political pressure for stronger protections. The image of the hammerhead, bizarre, beautiful, vulnerable, has become a symbol of ocean conservation more broadly. But time is running out. Hammerheads cannot recover quickly. Even under optimal conditions, with all fishing pressure removed, it would take decades for populations to rebuild, and conditions are far from optimal. Fishing continues, habitats continue to degrade, the ocean continues to change. The question is whether we will act quickly enough to save the hammerhead, or whether this extraordinary animal, perfected over 20 million years of evolution, will be erased in a single human lifetime. Part 7. Final thoughts. Let us return for a moment to where we began, to that female great hammerhead, hunting in the twilight waters off Cocos Island. She has just finished feeding on a stingray, the poison barb still lodged in the side of her mouth, a wound that will heal in time, leaving another scar among dozens. She turns and begins to swim, that massive head sweeping back and forth, already searching for the next meal. Around her, the school of scalloped hammerheads continues its circling dance, a living kaleidoscope of prehistoric forms that have changed little in millions of years. This scene, this moment of perfect predatory grace, has played out in Earth's oceans for as long as there have been hammerhead sharks. It has persisted through ice ages and warm periods, through mass extinctions and explosive radiations of new species, through the rise of marine mammals and the evolution of modern reef ecosystems. But it may not persist much longer. We have learned, over the course of this exploration, that the hammerhead's life cycle is a testament to evolutionary ingenuity. From the complexity of gestation and live birth, through the gauntlet of juvenile survival, to the decades of prime predatory performance, and finally to the slow decline of age. We have seen how the hammerhead's bizarre morphology is not a deformity, but a masterpiece of adaptation, each feature serving multiple overlapping functions. We have understood how these animals shape the ecosystems they inhabit, their presence rippling through trophic levels to influence species they never directly interact with. And we have confronted the sobering reality that all of this, 20 million years of evolution, the intricate machinery of sensory sophistication, the ecological relationships, the cultural significance, can be undone in mere decades by overfishing, habitat destruction and climate change. The hammerhead shark stands at a crossroads. One path leads to extinction, not with a sudden catastrophe, but with a gradual winnowing of populations until, one day, the last hammerhead dies and the oceans are permanently diminished. The other path leads to recovery, slow, uncertain, requiring decades of sustained protection and habitat restoration, but possible. Which path we take is not the hammerhead's choice, it is ours. The insane life cycle of the hammerhead shark is a reminder that evolution, for all its creative genius, cannot anticipate every threat. The adaptations that served hammerheads so well for millions of years, their slow growth, late maturity, low reproductive rate, their dependence on coastal nurseries and predictable aggregation sites, have become vulnerabilities in the Anthropocene. But it is also a reminder of resilience. Hammerheads have survived the challenges of deep time. They have adapted to changing oceans before. If we give them the chance, if we protect their habitats, regulate fishing, address climate change, they may yet adapt to this latest, most dangerous threat. Us. The great hammerhead glides through the darkness, her sensors scanning the seafloor, her body a 400-million-year-old solution to the problem of survival in a predatory ocean. She does not know she is endangered. She does not know that her kind is vanishing from vast stretches of ocean where they once thrived. She knows only the hunt, the eternal search for food, the imperative to survive one more day. We know more. We understand what is at stake. The question that remains is whether understanding will be enough, whether we will choose to preserve these magnificent animals, or whether future generations will know hammerheads only as fossils and fading memories, cautionary tales of what the ocean once held. The choice ultimately is ours. The hammerhead can only do what evolution has programmed it to do: swim, hunt, survive, reproduce. The rest is up to us. If you enjoyed this episode of Animal Uncovered, following the podcast is the best way to support the show. And if there's an animal you want us to uncover next, leave a review or comment and let us know. Until next time.